Hello and welcome to this video titled, Why Do We Need IPv4 Addresses? In this video I'm going to talk about an introduction to IPv4 addressing, so you'll learn the structure of an address and what it is. We'll break it down into network and host bits and understand why it's important to know the difference between those two. And we'll understand packet routing decisions based on the ability to look at the network and host bits of an IP address. All right, so let's start by talking about IPv4 addressing. So if you've studied IPv4 and you know anything about the IPv4 header that's placed in front of your data, you'll know that probably one of the most critical components of that IPv4 header is the source and destination address. After all, that's the main reason why we use IP in the first place, is to get packets between remote networks from a source to a destination. So let's focus in now on just those addressing fields, leaving behind all the other fields of the IPv4 header. So the IPv4 address is 32 bits wide. So that's how many bits it is end to end. So the source address is 32 bits, destination address is 32 bits. So right here, this is an example of how your laptop, PC, or smartphone sees its IP address. Of course, it sees it as a binary number. We don't talk about it as binary numbers, but this is how computing devices view their IP address. And that is right there, 32 bits if you count them end to end. Now, an IP address is a logical address. What does that mean? That means that something about this address indicates geographically where your system is right now. Now, geographical might mean it indicates somewhere in that address the department you're a part of, the floor that you're on, the room that you're in, maybe the section of the campus that you're working from right now. And so because of that, if you move your device around like a laptop or a tablet so frequently does, if you move from room to room or department to department or from building to building, your IP address will change, because an overall large computer network is subdivided into different sections, and each section has a different IP network. So part of this address is going to be the network portion of the address. Your laptop, your PC, when it sees this 32-bit number, has to be able to identify which of those bits represent the network that it's on right now. And if it moves to a different network, for example, if you disconnect from the Wi-Fi access point that you're on right now, and you move your laptop over and you connect to a new Wi-Fi access point in a different department, your networking bits will change. Your entire 32-bit address will change, but the part that's most critical to your laptop will be representing that it's on a new network. So this 32-bit address is subdividable into two different components. Left to right, some of the bits from left to right will be the network portion. For example, maybe this right here. Maybe these bits right here are your networking bits, and these bits right here are your host bits. And it's very critical for any device running IP, whether it be a smartphone, laptop, tablet, whatever, to be able to find where that dividing line is between the network bits and the host bits. So this pattern, so if theoretically, this is just theoretical right now, if this were my network bits right here, that would mean that if I'm constructing an IP packet and the destination IP address of that packet had this exact same pattern, that would mean that destination resides in the same part of the network where I am. Whereas if the destination bits is some different pattern, that would mean, logically speaking, that the destination I'm trying to reach is not in my section of the network, but a different section of the network, which would mean my packet would have to go through a router. The only network my laptop knows about is a network he's sitting on right now, which is this, as an example. Any other bit pattern is like telling my laptop, hey, go to Jupiter, go to Mars, go to the Nebula Galaxy. My laptop has no idea where the heck those things are. But what it does know is that in my network, in this network, there's a device with an IP address that starts out with this same pattern, who is a router, who is a gateway. And if I send my packet to him, he knows how to get it to those remote destinations. Now, we as human beings can't deal with IP addresses that are in binary like that. No problem for a computing device, but we can't work with that. So we sort of format this address. We look at it in a different way so it's something that's human readable that we can handle. So here's what we do. Step number one is we take that 32-bit pattern there and we divide it up into 4 octets. Okay, remember an octet is a grouping of 8 bits. So here I've just divided it into four equal pieces. Each one is called an octet or a byte. And then we say, okay, we convert each one of those bytes from a binary number into a decimal number. And then we put a dot between those decimal numbers to represent that each one of those decimal numbers represents 8 bits of binary. So you can see here, the 192, that's my first 8 bits. If you know anything about binary, you could add that up. You know the 128 and the 64 bits are turned on, giving us 192. The next grouping of 8 bits translates to the number 1 in decimal. The next group is the number 1 in decimal, and then the final octet in binary translates to 3 in decimal. So this is called dotted decimal notation, and this is how you will see and manipulate IP addresses, is using dotted decimal notation. But just be aware that whenever you go into any system, whether it be your laptop, your PC, a router, a switch, and you type in an IP address, even though you're typing it as dotted decimal in the background, that computing device is translating it into one big long string of 32 bits in binary. Okay, so as I mentioned, devices that have IPv4 addresses, whatever they are, whether it be your wireless thermostat or your refrigerator, has to be able to know what network it's on. It has to be able to differentiate the networking bits from the host bits. Once it's able to do that, that will help it determine, okay, now that I've created an IP packet and I'm going to compare the destination with the source, with myself. So anytime a laptop, PC, smartphone creates an IP packet, and it might be creating thousands of IP packets every second, every time it creates one, it compares the destination IP address with its own source IP address. And that device says, okay, well, of this 32-bit number which represents me, I know these first few bits are my networking bits. That's the group or the part of the network I'm in. Let me look at the destination. Are the same bits in the destination matching my group? In other words, are the networking bits I have the same as the networking bits in this destination? If the answer is no, then he says, okay, this destination is off network. It's not on my network, it's on some other network. I need to forward this packet to my router, a default gateway who is in my network who can get it out there. If the answer is yes, that means, oh, okay, I can speak to that guy directly. I don't need to get the router involved. An analogy I sometimes make is think of it like this. Imagine that you are standing in the middle of your street, okay? And I tell you, hey, I want you to, let's say your street is First Street. And I say, hey, I want you to talk to Bob on First Street. Well, First Street is your network. And you say, oh, Bob on First Street. Well, I live on First Street. He lives on First Street. Therefore, I can just shout, hey, Bob, are you out there? And if Bob's on First Street like me, he should be able to hear me shouting to him, and he and I should be able to talk directly. But if I say, hey, I need you to talk to Sally on 17th Street. Well, now you say, oh, okay, well, someone called Sally, great, but she's on 17th Street. That's not my street. You can shout as long as you want until the cows come home, and Sally's not going to hear you because she's not on your street. She could be in a different country for all you know. So in that case, where would you go? You would turn to the Postal Service. That's analogous to your router. And you'd say, hey, Postal Service, if I give you my message for Sally on 17th Street, can you get it there? And if the Postal Service knows what they're doing, they'll say, of course we can. So you give your message to them. That's like giving your data to your router. And then they somehow behind the scenes, you don't know how they do it, you don't care how they do it, they get that information to Sally on 17th Street. That's sort of like how routing happens with these packets. So here's an example, a more realistic or practical example here. So notice that we have Bob and Sally, and they have been able to identify of their own unique 32-bit addresses that the red bits are their networking bits. Now in this video, we're not going to go into how do they figure that out. Of this 32-bit number, how do I figure out which bits are my networking bits? We have another video coming up that will cover that topic. But let's assume that logic has already been done. And so Bob and Sally recognize that these bits here in red are their networking bits. So everybody on their network has that same pattern. Now, Bob and Sally happen to be in the library. So everybody in the library, when they get an IP address, the first few bits is going to match this common pattern. That's their networking bits. Now, down below, though, that's not the library. Down below, that's the biology department. So because that's a completely different network, their networking bits have to take a different pattern. Now, if Bob wants to send a packet to Sally, he's going to create that packet, and he's very quickly going to recognize by doing a comparison of his source address against the destination that Sally's address is in the exact same network as himself. So he can just use this switch right here to talk to her. They can just talk directly back and forth with that switch. Similarly, if Sam wants to talk to Sue, they're in the same network. They can just use this switch. But if Sam wants to talk to Sally or Sam wants to talk to Bob, very quickly going to recognize that, okay, Sam says this is my networking bits. The bits I'm trying to get to is this. Not the same pattern, different pattern. So now Sam is going to have to redirect his information to a router. And the router is going to have to somehow learn that this pattern right here is reachable via interface number 1, and that this pattern right here is reachable via interface number 2. Once the router knows that information, it can route packets back and forth between these two networks. So that concludes this video. Thank you for watching.